Good morning to all. Welcome to channel Firjan. See, today we discuss electric potential due to electric dipole. 12th standard, second lesson. What is the lesson name? Electrostatic potential and capacitance. Before we discuss what is electric potential, what is electric potential due to uniformly charged ring and uniformly charged linear rod, this all we discuss. In this lesson we discuss, in this video we discuss electric potential due to electric dipole. Electric potential due to electric dipole. See, first we discuss here what is electric potential and electric dipole. See, electric potential means, for example, this is the point charge or distance from the charge at point P. What is the potential now? See, Vp equal to kq by r. Kq by r is the electric potential due to point charge q or distance from the charge at point P. That is Vp equal to kq by r. Electric dipole now, it is the two equal and opposite charges. See, the electric dipole now two equal and opposite charges, two equal in magnitude opposite charges which are separated by small distance 2a. This is the center. See, from here to here a, here to here a, so totally 2a distance means two equal and opposite charges which are separated by very small distance 2a, we call it as electric dipole. It is the electric dipole. Dipole. It has direction. What is the direction of electric dipole now? Minus q to plus q. So means that we call it as electric dipole moment. So electric dipole moment now we can represent P. It is the product of charge and its length between them. See, electric dipole moment means electric dipole moment is the product of charge and its length between them. What is the length between them here? 2a, charge is q. So that is the electric dipole moment. It is vector quantity. It is vector quantity. Its unit na here, see, charge na coulomb and length na meter. So coulomb meter is the unit of electric dipole moment. It is electric dipole moment. Electric dipole moment, that is represented by P. P equal to Q into 2a. See, vector quantity, unit is coulomb meter. Its dimensional formula is charge na, here see, a into t, so means charge current into time, length na l, so atl. So that we can write m power 0, l power 1, t power 1 and a power 1. So this is the dimensional formula of electric dipole moment. See, electric dipole moment na, it is the product of charge and its length between them. It is vector quantity. Its unit is coulomb meter. Its dimensional formula is m power 0, l power 1, t power 1 and a power 1. Its direction is minus q2 plus q. This is the direction of electric dipole moment. This is the direction of electric dipole moment. This is the electric dipole and dipole moment. Dipole means two equal and opposite charges which are separated by very small distance. Electric dipole moment, it is the product of charge and its length between them. This is a basic information. Now see, we discuss what is the electric potential due to this dipole on the axis of electric dipole and perpendicular to axis electric dipole at any point on the space, that we discuss. First we discuss first case. See, on the axis of electric dipole, on the axis of electric dipole, at x distance from center, x distance on axis of electric dipole. On axis of electric dipole means, see here, it is the minus q plus q. See, electric dipole means two equal in magnitude opposite charges which are separated by 2a distance, to very small distance, very small. See, it is the center, it is a, it is also a. So this is the electric dipole. From center, see, from center x distance at point P, what is the electric potential that we want to find out? See, that we call it as on the axis of electric dipole, that we call it as axial line. Axial line. So axial line means the line which passes through center of the electric dipole and along the axis of electric dipole, that we call it as axial line. On axial line, what is the electric potential at point P, x distance from the center? So that we want to find out. See here, this is the axis. See, in this case, here at point P, two potential acting. One is due to first charge and second one due to second charge from potential. Why now? The electric dipole has two charges. One is minus q, another one is plus q. Due to minus q, what is the potential at P? Due to plus q, what is the potential at P? So that we can find out what is the net potential. So that net potential is the electric potential due to electric dipole at point P, x distance from the center of the electric dipole. See, for that what we can do now, here first we can find out V1. So means potential due to first charge. What is the first charge here? Minus. So we can write minus. See, minus due to charge now potential at P point. This distance is x, this distance a. So means total distance is from here to here x plus a. See here, it is x plus a. This is the distance between first charge to and point P. So what is the formula actually? Kq by r. So r means here x plus a. We can write here kq by x plus a. This is the potential due to first charge minus q. That's why we can write here minus q. See, due to minus q, what is the potential at point P? Minus kq by x plus a. Due to first charge, second charge, see this charge, what is the potential at this point? See here, from center to point P, x distance, q to a, q to p, x minus a distance. See this q2 here, this we can subtract, we get the this distance x minus a. What is the potential now here? K q by x minus a. This is the potential due to plus q. Due to minus q, minus kq by x plus a. Due to plus q, kq by x minus a. These two are the potential due to minus q and plus q at point P, x distance from the center. We write here, we net potential at P. Net potential at P. So V1 plus V2. V1 plus V2. So what is the V1 here? Minus kq by x plus a. What is V2 now? Kq by x minus a. Yes na? See here, kq is common, we can take common now. Here see, kq common. So potential, net potential equal to kq common now here. What we get now here? Minus 1 by x plus a, minus 1 by x plus a plus 1 by x minus a. This is the value. So minus 1 by x plus a plus 1 by x plus a. See here, cross multiplication, this and this, this and this and this and this. We get V net equal to what now here? kq. See, I write here minus 1 into x minus a plus x plus a by x plus a into x minus a. X plus a into x minus a. See here, a plus b, a minus b. What we can write? A plus b into a minus b equal to what? A square minus b square. Yes, now here we can write. See that one here, kq. See, minus 1 into x minus into minus plus a, here plus x plus a by x square minus a square. See, minus x plus x cancel. What we get now here? See, kq into 2a plus a by x square minus a square. It is the net potential at point P. See here, what is the net potential at point P due to electric dipole minus q and plus q at P na? Kq into 2a by x square minus a square. See, before that, electric dipole moment. So P equal to what we can write now? Charge into length between them. This is the electric dipole moment. See, electric dipole moment means it is the product of charge and length between them. So what is the charge here? Q, and length is 2a. So 2a, this is called electric dipole moment, which is always minus q2 plus q. So this here, see, q and 2a is there, so we can write, instead of this we can write p. So means we can write here v net equal to kp by x square minus a square, x square minus a square. See, now here this a is very small to x distance. See, a is very less than x, that case a square tends to 0. See, we can write here v net equal to, now v net equal to what we can write now here, kp by x square only. Why not? A square is 0, so that's why kp by x square. This is the final equation we are getting after simplifying. See, what is the net potential at point P due to electric dipole means kp by x square. See, one more here. So what is the relation between potential and distance now here? V is inversely proportional to x square. So that's why we can write graph here. See, potential on x y axis, x on x axis, distance on x axis, how it is now graph. So this is the graph v proportional to 1 by x square. This is the graph between potential versus x distance. Yes na? See, again once listen, is the electric dipole, it has two charges minus q plus q. See, due to minus q potential here p, that is this one, due to plus q potential at point p, this one. So net potential due to electric dipole at point p, what is the net potential? V net equal to v1 plus v2, v1 this one, v2 this one. Simplification na, kq we common here, minus 1 by x plus a plus 1 by x minus a. So cross multiplication are here, here we get this and this. Simplify, minus x minus minus plus a, x plus a, minus x plus x cancel, a plus b, a minus b, a square minus b square. See, kq here a plus a, 2a by x square minus a square. So v net equal to kq into 2a by x square minus a square, or we can write electric potential, electric sorry, dipole moment p equal to what? Q dot 2a. Instead of q dot 2a we can write p, kp by x square minus a square. See, this a is very small, already we discussed. Electric dipole means two equal and opposite charges which are separated by very small distance. 2a is very small, a means very small, so a very less than x. So that case a square tends to 0, so we can write v net, instead of a square we can write 0, v net equal to what? Kp by x square. See, what is the relation here now in between, where potential and electric potential and distance na proportional to, inversely proportional. So we can draw the graph versus graph between potential versus x na, it is the graph for potential versus x distance. This is the electric potential due to electric dipole on the axis of electric dipole. On the axis means on axial line. Axial line means the line which passes through center and along the axis, that line we call it as, this line we call it as axial line. See, axial line means the line which passes through center and along the axis, along the axis of dipole, axis of dipole, that line we call it as axial line. On axial line, x distance from the center at point p, what is the electric potential now? V net equal to kp by x square. That relation is v proportional to 1 by x square. This is the graph. Yes na? Now we discuss second one on the perpendicular bisector, on perpendicular bisector of electric dipole. See, x distance from the center, same here we can write on the perpendicular bisector, on the perpendicular bisector, perpendicular bisector of electric dipole. See, before we discuss on the axis of electric dipole, now on the perpendicular bisector of electric dipole, that we call it as equatorial line. Equatorial line. Equatorial line means the line which passes through center and perpendicular to axis of electric dipole. See, this is the minus q, this is plus q. See, this is the center. From here, this is a distance, this is a distance. See, the line which passes through center and perpendicular to axis, this line we call it as equatorial line. See, equatorial line at point m, what is the potential? X distance from the center, it is x distance from center. At point m, what is the electric potential due to electric dipole? That only we can derive now. See, now see here, due to this charge, what is the potential at m point? See, this distance is a, this x. This distance we can take small r na. It is the root of x square plus a square. Yes na? Due to this charge, what is the potential at p? So V1 I write. V1 equal to minus kp by root of x square plus a square. This is the potential due to minus q at point m. What is the potential actually? K q by r. So r is here root of x square plus a square. That's why we can write minus kp by root of x square plus a square. This is the potential due to minus q at point m. So due to plus q, due to plus q, what is the potential at m? We can write that is V2. Why now it is, we can take it as first charge, it is we can take it as second charge. Due to first charge, minus kp by root of x square plus a square. Due to second charge, what is the potential now? Here see, k, sorry, here kq, here kq, charge is q na. See, charge is q, so kq by root of x square plus a square. Here charge is q, kq by root of x square plus a square. Again listen once, this is the electric dipole, minus q plus q, which are separated by small distance 2a. See, an equatorial line means the line which passes through center of electric dipole and perpendicular to axis of dipole. That line we call it as equatorial line. On equatorial line, x distance from the center at point m, what is the potential that we want to find out? For that, here two charges is there, minus q plus q. Due to first charge, minus q, what is the potential? Minus kq by root of x square plus a square. Why we write here root of x square plus a square na? This distance is, when it is right angle triangle, it is x, it is a, it's automatically root of x square plus a square. So that's why minus kq by x square plus a square. Due to this charge, here distance is r equal to root of x square plus a square. See, due to this charge at point m, what is the potential now? Kq by root of x square plus a square. See, V net, what is the net potential? Equal to V1 plus V2. V1 plus V2. V net equal to, V1 is what here? Minus kq by root of x square plus a square. What is V2 now? Kq by root of x square plus a square. See, here minus kq by root of x square plus a square, here plus kq by root of x square plus a square. Both are same value now. This and this cancel. What we get now? Here see, V net equal to 0. Means, see, on perpendicular bisector or equatorial line, potential is same. Not only here, this point, this point, this point, this point, this point, at any point on this line, potential is same. So that's here, see, we can take here minus q, here plus q. See, here we can draw the plane. See, this is the plane. At a particular plane, see this one, see this point. See here, in this plane, potential is same everywhere. Here potential 0, here potential 0, here potential 0, here potential 0. Means the plane which bisects electric dipole perpendicularly, on that plane electric potential is same. That plane or that surface we call it as equipotential surface or equipotential plane. See, the plane which bisects, sorry, the plane which bisects perpendicularly the dipole axis and has same potential, that plane or surface we call it as equipotential surface. See once, this is the plane. In this plane, potential is same. That plane we call it as equipotential surface or equipotential plane. See the plane which bisects perpendicularly the electric dipole. This is the electric dipole which bisects perpendicularly and has same potential. That plane or surface we call it as equipotential surface or equipotential plane. See, due to electric dipole at x m point from the center perpendicularly, electric potential is same. So not only here, so this plane has same potential. That plane or surface we call it as equipotential surface. Equipotential surface, this is the electric potential due to electric dipole. What is the electric potential on perpendicular line? Zero or same. That plane or surface we call it as equipotential surface. Yes, now see, this is the electric dipole has minus q plus q. Due to minus q, this is the potential. Due to plus q, this is the potential. Net potential zero. That's why in this line, equatorial line, potential is same, zero. This plane or this surface is perpendicular to electric dipole axis. So that's why this plane or surface we call it as equipotential surface. In the same way, it has same potential. The surface on which electric potential is same and which is perpendicular to electric field or electric dipole, that surface we call it as equipotential surface. Equipotential surface, this is the electric potential due to electric dipole. Next, at any point on at any point at any point in space x distance from center, x distance from center, what is the electric potential? That we find out. See, x distance from center, that we can write it as here r distance from center. See, r comma theta. Theta is the angle made. For example, see here minus q, here plus q. It is the electric dipole. It is the center. See, this is the dipole moment. So with the dipole, for example, here we can find out what is the electric potential, or is this point, or this point, or this point, any point in space. This point we can take m point. This m point, here we can join, this is the distance r. This r distance makes some angle with the dipole moment. So that is here theta. Theta means angle made by the electric dipole, direction of electric dipole with radius r, that is theta. Here na some theta, here na some theta. So means this r is radius or distance, theta is the angle made by the direction of electric dipole moment and distance r from particular point. So that is the r comma theta at distance, at r distance from the center. See this point, what is the electric potential due to electric dipole, that we find out. See, for that, the dipole moment, electric dipole electric dipole p can be divided into two components, divided into two components. One is p cos theta and other one is p sin theta. How it is now? See here, it is p. This is the p, means electric dipole moment is, this is the direction of electric dipole moment. This p has two components. Which side theta is there? That is p cos theta. Other one is P sin theta. It is P cos theta. It is P sin theta. We have here two moments is there. Two electric dipole moments is there. This P is divided into P cos theta, P sin theta. For P cos theta, for P cos theta, M is axial point. Act as axial point. Axial point means this is the dipole. P cos theta is dipole here. On this will be axial point mean along the axis. Automatically this is perpendicular bisector. This dipole will be act as perpendicular to this one. So that's why P for P sin theta, M is equatorial point. Equatorial point. Due to these two, what is the net potential at M? So net potential at M is V P cos theta due to what is the potential due to P cos theta at axial point plus V P sin theta. What is the potential at equatorial point? It will be act as equatorial point. It will be act as axial point. See here, I repeat again, it is the electric dipole at any point in the space. I select this point or this point or this any point. This point I select. It is the all distance from the center. Theta, it makes theta angle from the dipole axis. So direction of dipole moment. So theta is the angle made by direction of dipole moment with radius r. R is the distance from center to a particular point. See, this point has, this is the R M point, this is M. See here, this P divided into two components. One is P cos theta, P sin theta. P cos theta, this one, it will be like axial point at, see for P cos theta, M is axial point. For P sin theta, M is equatorial point. Equatorial means perpendicular. See, due to that, what is the net potential at M? So due to P cos theta, one potential, due to P sin theta, one potential. So due to P cos theta, what is the potential now? Kp by x square. P cos theta by x square. We know already on axial line what is the electric potential due to electric dipole? Kp by x square. Here P cos theta is there. Kp cos theta by x square. On equatorial line, electric potential is 0. So what is the net potential now here? Right here. What is the net potential due to electric dipole at any point in the space now? See, at point M, K P cos theta by x square we get. This is the net potential at any point in space. Understood now this one? This is the electric dipole. This point, at particular point in space, what is the electric potential that we find out? We have two components here for this P divided into two components, P cos theta, P sin theta. P cos theta is along axial line, P sin theta is along equatorial line. Due to this axial point, what is the potential? This one. So equatorial point, potential 0. Net potential is Kp cos theta by x square. For example, if C, if theta is 0 means axial line, what is the potential now here? See, axial line, potential at axial line equal to theta, we can substitute here Kp cos 0. What is the cos 0? 1. So that's why Kp by x square. What is the potential along axial line now? So Kp by x square. For example, theta equal to 90, equatorial point. So V equatorial equal to Kp cos 90 by x square. Cos 90, 0. This total term is 0. So what is the potential on equatorial line? So 0. Already we know. So by using this we can derive the axial point and equatorial point also. So this is the general case. Before we discuss normal cases, this is general case for both equatorial and axial line. It is any case, any point, this point or this point, at any point we can derive an equation for electric potential due to electric dipole at any point in the space. Now, this is the concept, electric potential due to electric dipole. It is very useful to the who and all attempting the NEET JEE. Please see my videos, like, share and subscribe my channel. Thank you.